Lesson 1.2, rates of change using equations. So in lesson 1.1, we dealt with average rates of change, and we were able to estimate instantaneous rate of change using a table of values, as well as secant lines and estimating the tangent line on a graph. Today, we're going to be looking at getting an even closer estimate of instantaneous rate of change using an equation. So we have just a scenario here that we're going to think through for a second. We have a young gentleman who is going to launch a rocket, and he knows its trajectory. It's represented by the equation that we see there, which relates height and time. But he wants at 10 seconds, he wants this rocket to release a banner. So he really wants to know the speed that the rocket will be traveling at 10 seconds so that he can better design the banner that's going to fly out of it. This is a question that calculus can answer for him. Today we're going to get to the point where we're still estimating this rate of change, but we're going to be more accurate with an equation. You'll see what we can do there. So some notes for 1.2. For y equals f of x, that means we have the equation of the function, any equation, linear, quadratic, etc. If we have the equation, the average rate of change over any given interval, so from x value of a up to an x value of b, reading left to right on your coordinate plane, the average rate of change over the interval from a to b is determined by calculating what? You should remember, by calculating the slope of the secant line, or just the secant. What does that look like? That's the change in y over the change in x, which in our case is the value, in the numerator, we have the value of the function at b minus the value of the function at a. Okay, that's the difference in your y values over the distance in your x values. That's b minus a. Okay, this should be ringing a bell. I'm going to draw a picture to go along with this. We've got a graph here. Don't need any numbers on it. I'm going to draw a simple curve. Okay, this is a parabola. And so what we're saying is that if we want to find the average rate of change from A to B, we simply need a secant line, or it's just a secant, that intersects the curve at x equals A and at x equals B. So then our points of reference here, we can call them point P, which has the coordinates A, f of A, right? That's x and y, A and the value of the function at A. And then we have point Q. Again, P and Q are the main letters that we're going to use for arbitrary points on a curve. And the coordinates of Q are B and f of B. Now, what's really happening here? The slope of this secant line really is delta y over delta x, the change in your y value over the change in your x value. So we've actually created a right angle triangle there where the length of this side is b minus a. It's the difference in our x values. And the length of this side is the value of the function at b minus the value of the function at a. All right, so this is a quick catch-up review of what it means to find the slope of a line and use that to calculate the average rate of change of a curve. But something else we've already talked about is that we can get a more accurate estimate the closer and closer and closer that we bring Q to P. So if we slide point Q along the curve closer and closer and closer to P, then the secant from P and Q will be a much closer estimate of the tangent at point P. So what we're going to do is instead of using B minus A here, we're actually going to communicate point B with respect to the difference between B and A. And we're going to call that length H. Okay, so now you can see that as H gets smaller, our estimate is going to be more and more accurate. Okay, so here's what we're going to do. We're going to make a little note. Let H be the interval between A and B. And then we're going to express our values in terms of H. Well, what does that mean? It means we're going to take this exact same equation that we've already been working with, okay? But now, so let me copy it down, we've got the change in y over the change in x. But now instead of saying that we have the value of the function at b, b is actually going to be a plus h, okay? So now we have the value of the function at a plus h minus the value of the function at a over, and remember, instead of going from b minus a, we're going to go a plus h minus a. Okay, I'm going to simplify that out one step further. The numerator is not going to change. F of a plus h minus f of a. And in the denominator, I can see that I have a positive a and a negative a. So that's 0, leaving me with just h. I also need to note an exception here, then that h is never allowed to be 0. What does that mean? Well, if h were 0, then P and Q would actually be the same point, right? If I don't move at all along the curve, then P and Q are the same point. So h can't be 0, but it can get as close as we possibly can to 0. It can be infinitely close. And as a matter of fact, the closer we get h to being 0, the closer we bring Q to P, the closer an accurate estimate we get for the tangent line, which would give us the slope of the tangent, which would give us the rate of change, which for our gentleman trying to woo his girlfriend, he would get the speed of the rocket in that case. And this little equation right here, with change in y over change in x, is called the difference quotient. Okay, it's a quotient because it deals with division. It is a difference because it deals with the differences in the values and in the interval between a and b. This is a difference quotient. All right, let's dive into example 1. We're going to estimate the slope of a tangent by first simplifying an algebraic expression. So we've got Ahmed. He is cleaning the outside of the patio windows at his aunt's apartment, which is located 90 meters above the ground, and he accidentally kicks a flower pot. Sure. Sending it over the edge of the balcony. And we need to determine an algebraic expression in terms of a and h to represent the average rate of change of the height above ground of the falling flower pot. All right, well, the height of a falling object can be modeled by the function s of t equals d minus 4.9 t squared. Now this represents acceleration due to gravity. You have probably seen that used before, 4.9 t squared or 4.9 s squared or something like that. And so in this expression, all we need to know is the height. Obviously, as it falls from a higher point, it has opportunity to fall faster and faster and faster until it reaches what's the maximum velocity. At any rate, this is what we have, and we can sub in what we know, which is the original height of the flower pot above the ground, which is 90 meters. So we've got 90 minus 4.9 t squared. But we need to write this in terms of an average rate of change. We need a secant line in order to work with specific intervals that we're going to be dealing with in the next section. Okay, so a secant represents the average rate of change over an interval. And we know we can calculate the rate of change using our change of y over change in x formula, which in terms of a and h looks like this. The value of the function at a plus h minus the value of the function at a over the value of the function at b, which is, sorry, just a plus h. And we don't even need to do that because we already simplified it earlier. So we have just h in the denominator there. Well, from here, we can plug in what we know. We know what our function is. Our function is d minus 4.9 t squared. Okay, so we're just going to put that in, the value of the function, and wherever we see our variable, which is t, we're going to put in a plus h, okay, because that's the value where we want it. This is going to work for any interval over the entire time that the pot is falling to the ground. So here we go. We're going to have the value of the function at a plus h. Well, that is 90 minus 4.9. And wherever I see t, I'm going to put in a plus h as my variable. Minus the value of the function at a. So 90 minus 4.9 a squared. And this second guy needs to be in brackets. Okay, the denominator remains h. Now, in order to simplify this, I'm going to expand this binomial. I'm also going to distribute this negative sign. Okay? So here we go. We've got 90 minus 4.9. And a plus h squared is going to be a squared plus 2ah plus h squared. That's one of those patterns of special products that we should remember. We've got 90, that's a negative 90, and a negative times a negative is a positive, positive 4.9a squared. Let's rearrange this and group our like terms. And actually, we still need to expand this. We need to distribute the negative 4.9 to our trinomial before we do anything else. And this is also over h. So now we've got 90 minus 4.9 a squared minus 9.8 ah minus 4.9 h squared minus 90 plus 4.9 a squared, all still over h. We're still speaking in general terms, right? We're using our a and our h. We don't have a specific interval yet. And now we're grouping like terms. So we've got some a squareds. I've got negative 4.9 of them there, positive 4.9 of them there. That's easy. That's going to cancel out. I've got a negative 4.9 h squared. I've got a 9.8 ah, and then I also have a 90 minus a 90. Those are going to cancel out. So the only thing left in my numerator here is, oh, and look, our h's can cancel out, but we'll do that next. Negative 9.8 ah minus 4.9 h squared over h. And then I notice I have a factor of h in every single term, which means I can Cancel them out. Negative 9.8a minus 4.9h. This becomes the reduced, simplified algebraic expression for the slope of a secant over any interval with a pot falling from 90 meters, okay? In example 1.1b, we are going to use that equation to figure out the average rate of change between the interval of 1 second and 3 seconds after the flower falls from the edge of the balcony. So we just have, in this scenario, A, our first value is 1, and our difference, our H, is 3 minus 1, which is 2, okay? That's the 2-second interval after 1 second, okay? So between, let's plug this into our equation. We've got delta y over delta x. I've copied our equation here. Just going to sub in our known values. That's negative 9.8 times 1 minus 4.9 times 2. 4.9 times 2 is 9.8. And they're both negative, so we've got negative 9.8 minus 9.8, which equals negative 19.6. And that's going to be measured in meters per second. Okay, meters per second. The negative in this result simply indicates that the flower pot is moving down, okay, as opposed to up. In part C, we're asked to estimate the instantaneous rate of change at 1 second and at 3 seconds. Now, we can do that by bringing point Q as close as possible to point P. What does that mean? It means we're going to start with an A value of 1, and our H value is going to get smaller and smaller and smaller in order to most accurately reflect the instantaneous rate of change. Now, this equation is really helpful because I now don't even need the value of the function at a second point along the curve. Does that make sense? We used to need this point and the value of the function there, and we needed this point, and we needed to calculate the value of the function there in order to do change of y over change in x. With our new equation, in terms of a and h, we don't need this second point. We simply need to say that this distance, which is h, should be really small in order to get an accurate estimate on the instantaneous rate of change at point P, okay? So that's what we're doing here. I'm going to do 2 values of h for each of these values. And so just a quick table of values looks like this. Our a value is going to be 1. I'm going to try it twice to show that as we get a smaller h, we get a better estimate. So our h value, which is starting at a, and then the change, the distance here, the difference between the x coordinates, we're going to go with 0.01. And then we're going to try it again with 0.001, okay? Now, that means here we'll go with the slope of secant. So using our formula, we've got the slope of the secant is negative 9.8a, which is times 1, minus 4.9h, which is 0.01, sorry. And that equals, in the calculator, negative 9.75. Let's go ahead and do the same exact idea. We're going to take our secant, slope of the secant, expressed in a and h, negative 9.8 times a, which is 1, minus 4.9h, which is 0.001. And that comes out as negative 9.795. So 1 second after falling off, it's already moving at a rate of approximately 10 meters per second. Okay, now let's go ahead and take a look at what's happening 3 seconds after falling off. And go ahead and take a guess. Is it going to be moving faster or slower? Is the rate of change going to be, the absolute value going to be greater or less than 9 or 10? Okay, well, let's see. We're going to take 3. We're going to do it twice. We're going to first take a difference of 0.01. Then we're going to take an interval of 0.001. We're going to plug those values into the secant algebraic expression we have for the rate of change of height. That's negative 9.8 times 3 minus 4.9 times 0.01. And that comes out to negative 29.35. Again, negative 9.8 times 3 minus 4.9 this time times 0.001. And that comes out as negative 29.395. And so we can see that it appears that the slope of the secant at 1 second is approaching because we're bringing our points P and Q closer and closer and closer together. We're shrinking the interval, and we went from 9.75 to 9.79. That's approaching negative 9.8 meters per second. Well, what about at 3 seconds? At 3 seconds, our first estimate was negative 29.35, but then we brought our point even closer, made our interval even smaller, and we got 29.395. So this appears to be approaching negative 29.4 meters per second. Now, remember, we can't say definitively that the speed at this point is 9.8 meters per second, or that the speed at 3 seconds is 29.4 meters per second, because what that would do is that would negate that would make the change in h, that would make the interval 0, okay? And that can't happen. So we can get, using this type of math, closer and closer and closer and very close, and we can estimate and we can assume and we can say it's approaching this, okay? Part 2 of this example asks us about the equation of the tangent. So we're going to get an equation of a line. Well, to get an equation of a line, we need 2 things, right? We need a point and the slope. Now, we have already estimated the slope in the previous problem, okay? Our estimation for slope was negative 9.8, okay? What we don't have yet is the exact point that we're dealing with, but we can get it simply by subbing our value of interest into our original equation for average rate of change. Remember, not the original equation for the speed, okay, but the rate of change equation, which as we move along is going to relate to a derivative, but we don't know that word yet. So we'll carry on as this. So our rate of change, we need to know what the corresponding y value is for a t of 1, or what the speed value is, because rate of change corresponds to the speed that the flower pot is moving. So we're looking for the speed at 1 second, and I'm going to use the equation that we've been working with in part 1. We've got 90 minus 4.9 t squared. I'm going to sub in my known value 1 for t. 1 squared is 1, so I'm at 90 minus 4.9, which is 85.1. So the point of tangent, the tangent point is 1, 85.1. And we know that the slope at that point is approximately negative 9.8. If you'd like a picture of what's happening here, it's on page 18 in your textbook, okay? From here, we can get the equation of tangent using our point slope formula. We've got y minus y1 equals the slope times x minus x1. Sub in the values that we know. We've got y minus 85.1 equals slope, which is negative 9.8, times x minus x1, which is 1. And we're simply going to expand and simplify and put this in y equals mx plus b. But of course, we're not really dealing with y's and x's. We're dealing with s's and t's, but we'll sub that out when we're done. So here we go. Negative 9.8 x plus 9.8 on the right. Y minus 85.1 still on the left. Now I'm going to add 85.1 to both sides, leaving me with just y on the left, and on the right we've got negative 9.8x plus 94.9. We're going to put that in terms of s and t. And that tells us the speed. We now have an equation for the speed. The speed is negative 9.8 t. Remember, that just indicates that we're heading down. That's the slope and negative slope at this point, at the 1 second point, plus 94.9. And that is the equation of the tangent at t equals 1. Now, if we had to get the equation of the tangent at t equals 3, we would follow the same steps. That tangent line would be a different line. You could know already the slope is different. It would be much more significant slope. Let's say the relationship of the flower pot is kind of how I drew it here. We calculated the slope at 1 second. The slope at 3 seconds would be much steeper and have a higher y-intercept. You are responsible for practice problems from page 20, numbers 1 through 19.